Dear participants and respected speaker, a very warm good morning to one and all. I, Varlin Betty Cruz, Assistant Professor, Department of ECE, delighted to welcome you all on behalf of Gates Institute of Technology for the second day Faculty Development Program on Advanced Technologies and Challenges in Electronics and Communication Engineering, organized by Department of ECE, Gates Institute of Technology, Gutti. Ladies and gentlemen, and now I request Ms. G. Reshma Madam to introduce the Day 2 speaker.
Thank you, Madam. A very warm welcome to all for the Day 2 Faculty Development Program. This is Reshma, Assistant Professor from EC Department. It's my honor and privilege to introduce our Day 2 speaker, Dr. Avishek Adhikary. Sir, we extend a hearty welcome to you. Dr. Avishek Adhikary is an Assistant Professor, Department of Electrical Engineering and Computer Science at the Indian Institute of Technology, IIT Bhilai. He pursued his graduate BE in Electrical from Jadavpur University, Kolkata, and attained Masters from IIT Kharagpur and PhD from IIT Kharagpur, India. Sir has a wide area of interest in the field of research, which deals with smart sensors, intelligent instruments such as IoT, Internet of Things, lab on chip, machine learning, system modeling such as bioimpedance, COVID-19 pandemic, and in analysis and synthesis of fractional order system and in control theory. His primary areas of teachings are circuit and systems, control system engineering, design of analog and mixed signal circuits, sensors, measurements, and instrumentation, advanced and digital control system. Sir has also a very rich experience in academia. He took the responsibility as a member in Central Instrumentation Facilities since May 2021. He was invited to various talks such as Atal Faculty Development Program, Bitcoin 2020, etc. He has also an professional experience working as Assistant System Engineer in Tata Consultancy Services, Kolkata. Dr. Avishek Adhikary has been awarded by the Best Researcher Award in the year 2017 for Instrumentation and Signal Processing Specialization. He also received the Best Paper Award in the track MEMS Electron Device and Sensor in IEEE Tech System 2016 Kharagpur. Dr. Avishek Adhikary has published 8 journals, 6 conference papers, 1 patent, and authored 3 book chapters. Sir, we are very pleased and grateful to you for sparing your valuable time with us. Once again, we extend a hearty welcome to you, sir. Now, I request you to address the gathering. Thank you, one and all.
Thank you, Dr. Kavita, and thank you everyone who is present here for coming to this session. And I hope I am audible. So I will start on the topic. I think that sharing screen option is not activated for me. Can you please look into that? Yeah, thank you.
So you can try it now, sir.
Yes, yes, yes.
So we can see your screen, sir.
Right. Thank you. Thank you very much. Okay. So once again, I welcome everyone, all the esteemed faculty members and the participants to my talk. I'm really honored that in this occasion of the national level online FDP on the advanced technologies and the challenges in the electrical and communication engineering, I have been asked to present our research interests and our research experience to this revered gathering. That for that I am really what I can say, my pleasure, my gratitude to the GATE Institute of Technology, the Department of Electronics and Communication Engineering, and all the participants present here. So without further ado, I will start on the topic. My today's topic of the speech is on the fractional order electronics, a new domain in the circuit and control. So what is a fractional order? So we will start from that. So that is our more or less topic of discussion for today's. That is fractional order system, basic definition, fractional order system in nature to network, then fractal, the new circuit element, factors in all the four quadrants, then FO circuit theory in resonators, PLL and filters. Then we will go through a little bit of system modeling aspect on the fractional order system and from the MATLAB where we can use this fractional order toolbox. And then if when the time permits, I can highlight a few advantage of the fractional order system in the power electronics and fabrication of the single element fractal. So these are the more or less in which I will try to focus on different aspects of the fractional order system, which is a quite emerging system in nowadays in the cutting edge technologies. So we'll look into it. We will first familiar with the fractional order terms, and then we will look into how it is advantageous in the traditional circuits and electronics. Okay. So before we go into the fractional order system, as I just said, it is the emerging domain of the cutting edge electronics. So let's see that the matrices that how much interest, how much popular it is in the recent trend of the research and technology. So this is the few institute in the India in the last 10 years where different research group has initiated this research on the fractional order system. So which includes almost all the first generation IITs like IIT Delhi, Bombay, Kanpur, and IIT Roorkee, IIT Kharagpur, of course, a few NITs, NIT Silchar, NIT VNIT Nagpur, NIT Uttarakhand, NIT Raipur. Then there is the IIT Bhilai, IIT BHU, the later generation IIT. They also has taken this initiative. IIT Palakkad is there. So we can see that in India also about 20 institute. This research is going on the fractional order electronics. At the same time, all over the world, there are many institutes. I just have kept name of a few institutes only. Okay, I can clearly see that I have missed Brunel University and the Petra University, Brunel University of Switzerland, Petra University of Greece, with whom I have collaboration. So apart from that, there are the universities in Russia and Spain and Iran, China. So we can see that lots of universities, this research is going on nowadays. And this is the trend in terms of paper and publication. You can see between, it's not very new topic, but we will discuss in the upcoming discussion that why for a long time, the researchers was not much interested or what you can say, could not pursue this research, and how it suddenly become a point of interest and in a booming condition. So you can see in the year 1907 to 2000, there was a publication in the IEEE publication was this has to be IEEE actually, IEEE actually at that time, before the 1960s and all. So 12,917, and then between 2001 and 2010 the publication has increased. Now within 10 years there is a 3,600 publication, and in 2011 2020 the publication has increased to 5,400, almost 1.5 times. And you can see that nowadays, so every year almost 1,000 papers is coming in the IEEE only on the fractional order topic. So what is fractional order system, which came from the fractional order calculus? So what is the fractional order calculus? Basically, what we say, the fractional calculus is a generic definition of the calculus. What we know, that is basically an integer order calculus that is only a subset of the fractional order calculus. So when is the birth of the fractional order calculus? Is it a very new topic? No. We say the fractional order calculus born at the very same time of the integer calculus. We basically identify a particular letter as a birth point of the fractional calculus when Leibniz was actually communicating with L'Hopital regarding the higher order differentiation, and then L'Hopital asked that what if when the Leibniz was proposing this d2x, dt2 is a second order differentiation, d3x, d3 is a third order differentiation. At the very same time, L'Hopital asked Leibniz, later, it's not email, the real mail at that time. So what will be if the order is half? And then the Leibniz answered, it will lead to a paradox from which one day useful consequences will be drawn. So this is the story of 1680, and then almost 300 years passed, okay, before the fractional order calculus actually comes to the picture once again. Before we come to that point, that's why suddenly after a long time of oblivion, why fractional calculus becomes so much important in the last 2-3 decades. Let's first go through the basic definition of the fractional order calculus. So the one of the main what I can say limitation, or one of the reasons why fractional order calculus was not for a long time too much popular, the reason is that there is no single definition of the fractional order calculus. There are lots of definitions of the fractional order differentiation or fractional order integration. Out of them, mostly 3 is the most popular one, and all other definitions can be taken as a special form of these 3 definitions. The first one is Riemann-Liouville definition. We all know the concept of the Riemann integration. So this Riemann-Liouville definition was actually proposed by the Riemann with collaboration of the corollary coming from the Liouville. So that's name is the Riemann-Liouville definition, which says, basically, before I start, let's say that what is the fractional order differentiation? It's the differentiation of the order say 0.5 or of the order say 0.7. So how to find out a half order differentiation or 1.5 order differentiation? Riemann was saying that you integrate it with say up to 1 order, then differentiate it back to between, say, if it is rth order, then differentiate it back to the n-1 to rth order. Okay, so it is saying that you integrate fully and differentiate partly, and overall thing is that a fractional differentiation. These are Riemann's definition, where the Caputo is saying, I mean, here the idea is that first you integrate and then you differentiate. That is the Riemann's definition. Caputo's definition is opposite. He said first you differentiate up to fractional order and then you integrate. All this differentiation and integration is involving the gamma function. This is the expression for the differentiation and the integration. But unfortunately, it looks like quite cumbersome, quite complicated. And even whatever I am going to say that first integrate and then differentiate clearly, evidently it is not very much clear to any of you guys most probably. I am not also intending to go much details on this point, Because this official definition, although I have introduced, we are not going into this path. For us, the electrical engineer, we want to see this thing in terms of Laplace domain. So we will slowly move to that domain. I just want to say that this was the continuous time differentiation. This kind of, or if anyone is interested in the derivation of the mathematical analysis, he will be interested in this different definition. And accordingly, we can find out a fraction of the differential equation. So just like we denote as a dy dt and all these things. So here it is a generic format. A dt r means this is a generic format of fractional differentiation which take part of both differentiation and integration in the fractional order, which means if it is r is greater than 0, then it looks like d power r dtr is a fractional differentiation. If r is less than 0, it is denoting a fractional order integration, and if r is equal to 1, it is especially an algebraic equation. Okay, A stands for the initial condition. Here for both differentiation and integration, initial condition is important because in the definition, both integration and differentiation is present. Now with this, we can have some particular kind of differential equation of the fractional order. So it is an differential quantity with order alpha power n, alpha n. It's a differential quantity with order alpha n minus 1, something like that. And once we convert in the Laplace domain, what we are getting all these fractional differentiations, so d power alpha, they simply become s power alpha. So d power alpha n becomes s power alpha n, d power alpha n minus 1 becomes s power alpha n minus 1, d power beta m becomes s power beta m. Okay, so a fractional differential equation in time domain can easily be represented in the Laplace domain because fractional system is a linear system. So Laplace operator can be applied here. All the coefficients are following the homogeneity. All the coefficients will be attached. So an is here. The d alpha yt dt becomes s power alpha. That's all. And then the superposition also holds. So all the plus terms will be there. Okay. So then the transfer function is going to be just as we can define from here, us by ys by us, it is going to be bm s power beta m plus bm minus 1 s power beta m minus 1, and that goes on. Of course, they are rational function, and accordingly we can find out the transfer function of any system or transfer function of a signal or whatever we will require. So this we will be focusing in the upcoming discussion. Then just like we can do the Laplace transform of the fractional system, we can do of the we can also do the inverse Laplace transform of the fractional system, which is especially known as Mittag-Leffler function. So if we know the Laplace transform of the fractional system, we can carry out all the relation, and if we really need a time domain analysis, we can always use this Mittag-Leffler function, which is also available in our MATLAB toolbox. We can use Mittag-Leffler function, and from there we can find out the time domain response. This slide is only to inform you that you can carry out the entire calculation in the Laplace domain. Ultimately, there is a tool which can also bring back the entire analysis in the time domain also. Okay. So once again, what is a fractional order system? It's a system which can be defined with a transfer function in which the power of s, that is a Laplace operator, is a fractional number. That is a basic definition of a fractional order system. Okay, it's not that it has to be carried out only the transfer function model. It can also be carried out in the state space model. Of course, the state space model means it is in time domain, so we will be requiring the Riemann-Liouville or Capot definition, or we will be requiring Mittag-Leffler definition. For today's discussion, I am not going into the time domain discussion. Therefore, we will be not focusing on the state space model. We will be mainly focusing on transfer function model. But the fact is that state space model is also available and valid for the fractional order system. So in this phase space model, it looks like, you can see these are controllable form of the phase variable representation. Here, instead of usually we used to write x1 dot x2 dot x3 dot like that, here is going to be fractional differentiation of x1, fractional differentiation of x2, fractional differentiation of xn, and here is the corresponding standard canonical form x1, x2, xn, and this is the B matrix, is a C matrix. That this part is completely same as the interior space model. Only here we can see instead of x1 dot x2, we are going to have some fractional differentiation expression. That's all. Similarly, fractional system, this is the initial condition, because all space model comes with the initial condition. So you can just simply give the initial condition. Here is no speciality in between, no difference between the fractional differential equation and the interior differential equation. It is going to be the same, and same format, same observability matrix, same controllability matrix. So there is no difference between the space model of the fractional system and the approach of the space model of the fractional system, in the approach of the space model of the interior system. Okay. Similarly, this discussion can be extended to the fractional nonlinear system. The basic idea of the nonlinear system is that the differential equation is not only a function of x1, x2, it is also a function of t that can also be incorporated in the fractional system, and no other change is required. So up to this point, this was the initial few part of today's discussion. Up to this point, what I have wanted to establish, that there is a calculus or corresponding definition of the system which we call fractional system, which is based on the fractional differentiation and the integration. There are defined definition for them, although there is a set of definition, that is one of the complications of the fractional system, but that complications can be avoided if we move to the transfer function model, because in the transfer function model, whether it is a Riemann definition or whether it's a Capullo definition or whether it is a Grunwald-Letnikov definition, it doesn't matter. All d alpha x, dt alpha, this kind of fractional differentiation becomes s power alpha term. And there is no problem to carry out our discussion in the Laplace domain, because just like an inverse Laplace function for the interior system, in the fractional domain also there is an Mitter-Clifford function which is also available in the MATLAB command, by which we can convert the Laplace domain analysis into the time domain analysis at the end to get the time response in the fractional of the fractional system. Okay, this was one part. Second part was that, of course, apart from transfer function model, the entire analysis can be carried out for the space model, because transfer function model is not valid for the truly nonlinear system, which cannot even be linearized. So we will be requiring a space model for the nonlinear system, and it can also be carried out nonlinear system as well. So this was our basic platform. Now let's see why suddenly, when we are so much comfortable and complacent with the standard classical theory of the control electronics and circuit, why it is really required to suddenly enter into a new domain. So that comes from this catch line statement that fractional order system in nature, that the entire nature is in reality fractional. So let's start with few examples. So can we identify what is this? This is basically an ultra capacitor, okay, or the supercapacitor. In commonly, you can see this supercapacitor. So this supercapacitors, how this supercapacitor behaves, why supercapacitor store charges. Of course, these things can be explained from the point of the chemistry and a set of differential equation. But the thing is that all those chemistry and set of differential equation cannot exactly describe the supercapacitor nature until and unless those differential equation is realized in the fractional order domain, or rather you can say that all the dynamics of the supercapacitor is aptly described with fractional order differential equation. The next figure I can see here is a fractal structure. So anything which is following this kind of fractal structure, many reports, many literature, you can go and see, they are properly explained when we adopt a fractional order calculus. The third one, we all know what is this. This is basically a foam, okay, or these matrices. You can see that we press our hand on the foam or the matrices, it get displaced, it deformed, and then due to this elastic property, it regained. Now, nowadays, all of you guys, I think, know that a different company, this mattress selling company, they are claiming that they are selling a memory mattress. That means you sleep in the bed, and your bed remember your body shape. So accordingly, you are going to avoid a certain kind of spondylitis and all these things. So why it is not? It is actually violating kind of elasticity property. Why a memory foam can retain your shape? How can it memorize? If you really want to model this kind of system who can memorize, then you will be required the fractional system, because I will show the fractional system inherently can remember infinite number of time constants. Okay, as I was saying, it can remember. That is why fractional system nowadays very much essential and pivotal if you want to model the lithium ion battery or any kind of battery, for example, battery of the electric vehicle. So you know that in terms of electric vehicle, there is a term called SOC and SOH, state of charge and state of health calculation. So they are also, the fractional system can only identify correctly that what is your real state of charge of your electrical vehicle battery. In 1922, that was very important for us from the electrical engineer. Gic, you might have known this name. Gic first proposed or bring the fractional order system in the electrical engineering domain, where he proposed that all the transmission line, distribution line matrices can be more aptly designed with fractional order calculus. However, at that time, there was not enough simulation software and all the steps available for the fractional order system. So therefore, although he said proposed these things, for a long time we did not went to that domain. But it was the inception of the fractional system in the electrical engineering domain. Nowadays, not only the electrical engineering, you can see all kind of distributive system, whether it is a Lance parameter system, whether how a drug can be induced in your body, or any kind of chaotic system. That if how the virus is, that is why just in my introduction it was say that I modeled the COVID-19 pandemic. So that was also with the help of the fractional order system. But when a virus propagates, how that virus model will be, I mean, how the virus will propagate it, what will be their peak, what will be the zone, and which domain should be locked down, and all these things, those can be aptly described with the fractional order model. Not only that, I can even show you the share market picture, that the ups and downs of the share market, the prediction level is also, there are papers on the using the fractional order dynamics. So you can see the real world is fractional. And from there, this point comes, the engineer comes to say that if the real world is fractional, then all the events and the phenomena are fractional, then why not their controlling should be fractional? So from that point of view, in 1980s, the first came the fractional order controller. Okay. Although before 1980, there was a happening in 1960 when Bode actually lamented on a particular fact that this is called Bode's ideal controller. Bode said that he needs for a particular type of DC motor, he wanted to design a lead lag compensator, and he need a correction of 6 dB per decade. But you know that for any kind of transfer function, they cannot offer you 6 dB per decade fall. They always give you 20 dB per decade fall or 40 dB per decade fall. So there is no chance of 6 dB per decade fall. So he lamented on this point, and he said if there is a system for the 6 dB per decade fall, then I could have made an ideal controller for the DC motor. From that point of view, in 1960, the research further went on, and in 1980, Ipetra actually proposed a fractional order controller which can give you 6 dB per decade fall. We will see that thing also in the upcoming slide. So from 1980s, on the soil of the fractional order calculus, this tree continuously growing. You can see there are a leaf of many things in the domain of sensor, electronics, and control. I can show you some of the advantages. For example, FO resonator, they give very high quality factor. Actually, I will show you the theoretical. They can give infinite quality factor. FO oscillator can oscillate much higher frequency than the standard standard integer oscillator. Then there is F4 robust controller, which can show you isodamping property that I will show you in the scope of the converter. Then there is F4 PID controller, which offers us two extra design variables, and F4 PLL, which can offer a larger capture range. So there are, of all the domains has some advantage, some special features. I am not going to everyone, but of course, this is not, this is the this figure is also some 5 years old figure. There are more leaves, as more branches has come down within these 5 years, and just continuously growing with their unique advantages. So more or less from this part of the discussion, I can take some takeaway that all the distributive systems and the massive systems are fractional order system. Fractional order system has infinite memory. I will explain these things later. Then arbitrary order integration and differentiation is possible now, which give us a magnitude plot with the slopes of 20 alpha dB per decade, where alpha is my fractional order. So if my alpha is now 0.3, then 20 into 0.3 is 6 dB per decade. So therefore, I can have a magnitude plot of a particular transfer function which can give me 6 dB per decade fall or rise. So therefore, Bode's ideal controller can be designed. However, now there are a few questions. That first of all, what advantage of these unique features offer? Second thing is that this I have already mentioned. The second thing is that how to cast the dynamics in the designable side. I am talking about some mathematics. I was talking about some Laplace transform, but everything is a mathematical theoretical model. How can we get, we the electronics engineer, how can we catch these dynamics in some electronic component? We have resistor, we have capacitor, we have inductor. They represent algebraic equation, integration, and differentiation. Who is there who can represent the fractional order differentiation, fractional integration? That is our main challenge. And from that main challenge comes the fractal, the new circuit element. Okay. So the first one is, of course, I was just talking about the resistance. So first one is resistance, which in the Laplace domain, the relation of the voltage current relation is Vs is equal to Ris, right? So it is representing an algebraic equation because s power 0. Then the next one is capacitance. Vs is equal to 1 by SCIS, right? So here it is representing an integration because it is showing 1 by S, and the lastly it is Vs equals to SLIS. Related the voltage with some kind of differentiation. So next comes this fractal, who is basically connected with Vs equals to 1 by S power alpha F Is. So here in the voltage current relationship, I can see the impedance function is basically 1 by S power alpha F. And just in the previous discussion, I have shown that S power alpha stands for a fractional order differentiation. So this particular element is called fractal or fractional order element. In some paper, it is also called pseudo capacitance, fractional order capacitance, or constant phase element. I will explain all the meaning of this name. The idea is that this impedance function ZF is equals to 1 by F S power alpha, and within our scope of the electronic component, this alpha can be between anything between 2 and minus 2. Okay. This is a particular element. I will show that how to make this element. But if you have no scope to make this kind of element, we can always, our students can always make fractional element with an array of the infinite RC ladder. Okay, so this is a particular type of Foster-1 structure for realizing RC ladder. So this is we call single component fractional element. This is we call multi-component fractional element. Both of this kind of realization is quite famous and popular in the literature of the fractional system. Now let's understand the dynamics of these impedance elements. Zf is equals to 1 by fs power alpha. So Zf is equal to 1 by fs power alpha. So that in the frequency domain, s power alpha is going to be represented by j omega power alpha, which is going to be 1 by f omega power alpha cos alpha pi by 2 minus j sin alpha pi by 2. That is 1 by f omega power alpha with an angle minus alpha pi by 2. So let's see that is minus alpha pi by 2, that is minus 90 alpha. It is showing that this impedance element is always going to give us a phase at minus 90 alpha. So if the alpha is say 0.5, it is going to give me a constant phase at minus 45 degrees. Okay. Let's see the figure of that. So it is going to give me a phase of minus 45 degrees. So some of you may ask me that what is the speciality of this? We can always get minus 45 degrees if we go for some kind of RC circuit at a particular frequency. Now that is the catch. At a particular frequency, you cannot get minus 45 degrees at all frequency. Here, this particular element is going to offer minus 45 degrees at any frequency. Okay, so this is like an inductor who is going to offer you plus 90 at any frequency, or a capacitor minus 90 at any frequency. So it is going to offer minus 45 degrees at any frequency. Okay, now there may comes the second question, that what is the advantage of having such kind of constant phase for any frequency? That is a different thing. But first, let us appreciate this first unique feature, that it is going to give a constant phase for any frequency at any desirable phase. So if alpha is equal to 0.5, it is minus 45. If alpha is equal to minus 0.2, it is minus 18. Alpha is equal to minus 0.2, it is going to be plus 18. This kind of feature was not available at present in any kind of traditional circuit element. Okay. Now let's focus on the magnitude. So log mod z is going to be minus log omega minus log f, right? So if I draw this thing in the log graph or in the dB graph anyway, so its gradient is going to be minus alpha, tan alpha is going to be alpha, and in the decibel graph it is going to be 20 alpha dB per decade. So therefore we can see its magnitude is falling at 20 alpha dB per decade. So earlier all the system magnitude falls at 20 or 40 or 60 alpha dB per decade. Now the alpha is a fractional, so it can fall in 6 dB per decade or 11 dB per decade, something like that. Okay, this F we call the fractance. Just like there is a capacitance, there is an inductance, there is a resistance. The element is factor, its coefficient is fractance. Okay, and its unit is mho second power alpha. Okay, now mho is okay. It's just we are comfortable with mho, just like a conductance type of thing, because it is 1 by f type of thing is there. But what is second power alpha? Alpha is an order, so it is going to be second power 0.5, second power 0.8. What's the meaning of that? Let's come to that point. But before I come to that point, let's see the whole picture. Then only we will understand what's the meaning of second power alpha. This is a whole picture which we call the 4-quadrant impedance element. And in this 4-quadrant impedance element, 4 elements we all know. At least 3 elements we all know. 4 maybe many of us already know. What's the 4 elements? So first of all, one is a resistor. Basically, resistor is not a new element. If I can claim the resistor is also a fractional element with a very typical value of alpha equal to 0. Am I wrong? No, it is really like that. If we put alpha equal to 0, then Zf is going to be 1 by f. Therefore, this is a simple and value. That is Z is equal to R. So R here stands for 1 by f. So basically, what we call as a resistor is only a special case of the fractional element. Similarly, if we put alpha is equal to 1, it is going to be 1 by fs, a very similar thing to the capacitor. And if we put alpha equal to minus 1, it is going to be an inductor, a similar case as we can see here in this line, the red line. And also, this is matching the phase plot, because as we see that the phase is going to be minus alpha 90. So therefore, alpha equal to 0 into 90 means it is giving me 0 degree. Alpha minus alpha 90 means minus 1 into minus, it is plus 90 is inductive, and plus 1 into minus 90 means minus 90 is the capacitor. And there is also frequency dependent negative resistor FDNR, which stands for alpha is equal to +2 or -2. It doesn't matter, either you go in this direction or you go in this direction. So we all know these four traditional elements who are actually four axes of these four quadrant impedance elements, but there are innumerable number of lines between all these axes, right? And all these lines is basically one factor. So this particular line, which may stands for the phase angle, so this is a 0 degree, this is a 90 degree, so it may stands for the phase angle 30 degree, which means alpha is equal to 0.3. This is minus 30 degree, alpha is equal to 0.3. So clearly every line is one kind of fractal, and accordingly the fractal can lie in this first quadrant, where their corresponding phase, constant phase, will be between 0 and 90 degree. It may be in second quadrant, constant phase between 90 to plus 180 degree, third quadrant 180 to 270 degree, or the fourth quadrant 270 to 360, or in other words 0 to minus. So classically we can say this is an inductive type of factor. Okay, inductive type of acute angle factor, inductive type of obtuse angle factor, inductive type capacitive type of acute angle factor, or capacitive type of obtuse angle factor. Okay, or more simpler way, just following the quadrant, we can see the type 1 factor, type 2 factor, type 3 factor, and type 4 factor. But what is the main essence of these slides, of this topic? The thing is that factor is not a new circuit element. Factor is basically a generalized circuit element. Whatever we have learned, constant phase element, these resistor, inductor, capacitor, D element, all are constant phase element. Factor is also constant phase element. The entire idea of the constant phase element is not a new thing. It is it was always there. We were just focusing on 4 particular element of the circuit element, but now with the definition of the fractional element, with the what I can say, appearance of the fractional element, now we come to the concept of the generalized circuit element. So fractional element is not a new thing, neither an obscure thing. It is basically a generalized concept of the circuit element. Okay. Now let's focus on the unit. So as I have mentioned, the unit of the factor is mho second power alpha. Okay, or some guys can say as a farad second power alpha minus 1. Let's see how it is coming in terms of mho first. You can see that unit of resistance is ohm. Okay, then unit of our conductance is mho. Then unit of inductance, Henry, is basically ohm second. So inverse of Henry is going to be mho second power minus 1. Then inductance of capacitance is mho into second. So what I want to say, that capacitance is mho into second, inverse of inductance is mho into second power minus 1, and in between them, this is the unit of fractance, that is mho second power alpha. So unit of factor f is equal to second power 0.5, if alpha is equal to 0.77 second power 0.7, and alpha is equal to minus 1.7 mho second power minus 1.7. So this mho into second, this structure is matching with mho into second structure of the capacitance or inverse of inductance. But what is now the next question, that if the factor is one element, then why each unit varies for different alpha? Because if the unit varies, the dimension varies, it's not supposed to happen. And the answer is that no, factor is not a one type of element. You can clearly see from this figure, there are innumerable number of factors. Factor is a group name within which different type of element is there. Basically, even a resistor is also one kind of special kind of factor, or the inductor is also special kind of factor. So that is why a factor with an alpha equal to 0.5 is completely different type of element with a factor with an alpha equal to 0.7. Therefore, their corresponding fractals must have different dimensions. So that is the meaning of that, why even we are naming as a factor, they have different dimensions, because factor is a common group name, nothing more than that. Okay. Now the question is that what fractional power of S signifies? Here the second power 0.5. What is the meaning of that? So the answer is that it signifies that it remembers the history from the inception of time. And it's not only remembering, say, 5 seconds before, or it's neither remembering, say, 10 seconds before instance. It is remembering from just precedence 0 minus to the infinity, minus infinity time. Why so? That we will see during the realization. Okay. Now, why realization? So I think that by this time we are now comfortable. Let's go through once again. We are now comfortable with this definition of the fractional element. Then we understand their phase plot, then their magnitude plot, and then the concept of the generalization of the circuit element. And then we are somewhat okay with their unit of the fractional system, but we are still struggling with the meaning of the fractional, the significance of the fractional time, fractional second. What is the physical significance of the fractional second? That is our takeaway point from here. Okay, so let's move. So next, our challenge is that, okay, I understand how the factor of fractional element can be defined. The thing is that how to realize. Definition we understand in the domain of the circuit theory, how to realize for the practical aspect. But the factor design, which is now the hot topic of the last 20 years, has now two ways. One is multi-component factor design, and the second one is single component factor design. The multi-component factor design is almost started 50 years back or 60 years back, from the starting of the 1960. If I am not very much wrong, 1961 was the initial work, and then 1967, 68, the first formidable work came. But single component factor design is quite recent, something about 2005 onwards. Okay. A multi-component factor design is also has two parts: passive network-based design and active circuit-based design. Passive network-based design only takes the element of the R and C or L, where active circuit-based design includes some op-amp or MOSFET or OTA or OTRA. So this kind of active element. Okay. What about single component factor design? The multi-component factor design basically reuse the traditional electronic element and emulate the fractional other nature. But single component factor design starts the working from the first principle. So we don't reuse any kind of traditional electronic element, rather it develops the fractional element itself from the physiochemistry of the different kind of system. Okay, so that is a single component fractional element. Now, the practical specification of the factor or the practical factor. So we have already seen that factor must have a constant phase element, and it will fall down their magnitude with 20 alpha dB per decade. But a practical factor does not follow this nature exactly. The practical factor, let's start with the phase plot. It is not exactly straight line, it is rather the oscillatory. So this oscillation, we consider this, okay, it's a constant phase. We consider that like that. Okay, it is not going to be completely straight line. Of course, the smaller the oscillation, the more ideal the factor is. The second point is that even it is not constant for the entire zone. Okay, for a wide zone, it has to be constant. Otherwise, there is no difference between a simple RC circuit with a factor. But of course, beyond this zone, the phase considerably deviates. But this is not a very new thing. If any of you guys has tested a phase nature of any resistance over the large frequency, you will see at very high frequency or the resistive element becomes capacitor. So you just take 10 ohm resistance, you will see it showing 10 ohm resistance, say up to say from 100 millihertz to say 1 megahertz, then or 500 kilohertz, then suddenly beyond 500 kilohertz, it's becoming capacitive, and it becomes capacitive by 10 megahertz. So it is a new thing from the point of the circuit element. So just like the other circuit element, resistor, capacitor, inductor, fractal also has a certain zone of the operation. This certain zone of operation we usually define from the concept of the constant phase. So as long as its phase can be constant around a certain value, we call the constant phase zone, and that is going to be my operating zone or fractional error zone. Okay. At the same time, within that range, what is its maximum range of deviation from the mean value? That is called usually the phase band or PB. So smaller is the PB and wider is the CP zone, more ideal a practical factor is. On the other hand, similar nature can be seen in the magnitude plot also, but I have already defined the concept here, so I am not introducing the same concept in the magnitude plot. So although the traditional ideal factor has two specification, one is alpha and another is f. Alpha is the order and f is the factors. Now, from a practical point of view, we comes upon with few more specifications like the constant phase zone, which will be defined by the lower limit of the constant phase zone and the higher limit of the constant phase zone, as well as the phase band, that is the amplitude of the constant phase zone. And there is some basic mathematical data analysis, how which from a practical factor we can find out what is my constant phase zone, what is my phase band, what will be my alpha, and what will be my factor. That's very easy and clear. So now comes our first type of realization, that is the passive type of realization, passive type of multi-component realization, in which the most famous one is the RC ladder-based multi-component factor realization. The basic idea of the RC ladder-based factor realization comes like this. It was actually given by the Sheriff in 1990. That is, if we go for RC, we need this kind of 20 dB per decade fall. If we can have a multiple pair of pole zero cluster at different time constant. Okay, so one pole zero here at one particular time constant, another pole zero here is another particular time constant, the third pole zero is here in this particular time constant. Then what will happen? For a zero, it will be for initial pole and zero position, it is going to be zero, and then a sudden fall. Then again, it is getting a second zero, it is becoming straight, and the pole is falling. Then suddenly a closed zero, it is becoming straight, and then again for pole, it is falling 20 dB per decade. But the overall fall is now depending upon the position of the pole zero, the gap between the pole zero on the frequency axis, the overall gradient is going to be much different than the 20 dB per decade. It is going to be an average of that, and it is going to be 20 alpha dB per decade. So there are lots of proofs, papers on this realization, and following that, there are many guidelines. How can we realize? So these guidelines start from Douglas. Douglas and Lerner technically did not give any guideline. They basically was saying that this kind of thing is possible. Carlson was first gave some kind of circuit structure. Then S.C. Dattarai from IIT Delhi, he was very famous. The fractional domain realization in 1966 and 67 gives a prominent guideline to design alpha is equal to 0.5. Then comes the Oldham and Josky in 1983, who give the guideline for any alpha. Then Sheriff, who was famous for introducing calculation of F in that guideline. So now we said the four specification was there, alpha and F. Then Austerlitz came, who expressed this guideline from the transfer function model. Then Valsa and Vlach came to introduce the constant phase domain. So basically, Oldham gave the guideline for any alpha. Then Sheriff introduced the F. Then Valsa and Vlach actually introduced the constant phase zone. And in 2015, I proposed a guideline 15 and 19. I proposed a guideline 19, the combination of guideline in which also I introduced to attain a given specification on the phase band, that is the amplitude of the oscillation. So together, actually, we have proposed a guideline. So this last guideline, what I have proposed, in which all the specification now can be attained. So, and that can be actually this guideline can be simply write in the MATLAB code. So what will be happen in the MATLAB code? You will give your desired value of alpha, desired value of F, desired value of lower zone and upper zone of your operation, and maximum allowable oscillation in the desired zone. You can give that guideline, and it will return you back the value of R and C you really require. Okay, so this paper includes that one. It has a guideline with the corresponding MATLAB program. So that MATLAB program you can copy and run in your system, and it will give you a state of R and C, which if you arrange in this following structure, so it will give you how many number of R and C will be required, what will be the value of each R and C, and once you put it, so these are the calculations, the proposal, mathematical derivation which is included in the guideline. So we need not to, anyone need not to worry about that. They only have to copy the program from this paper and has to run, and they ultimately will get, for example, I have chosen a specification alpha equal to 0.6, F is equal to 10 microunit, if a lower frequency zone is 10 Hz, upper frequency zone is 100 kilohertz, and allowable phase band is 1.5 degree, which means my fractal, what I am going to design, that has alpha equal to 0.6 means it's supposed to give a constant phase zone around 54 degree, and that constant phase zone supposed to lie from 10 hertz to 100 kilohertz, and it have the allowance of plus minus 1.5 degree, that is from 52.5 to 55.5 degree it is allowed to oscillate. So for that program return back these R0 R1 values. So although these are very typical value, but you can always approximate with some kind of closed resistance value. Those are available, a closed capacitance value. I can show you this is the Ltsp simulation. Okay, and this is the Bland-Altman analysis, from where we can see that the whatever we have required following this value, we can emulate the system in the Ltsp, and we can get the exact response whatever we have required. So around the 54 degree, and the magnitude plot is falling with the corresponding F value. Okay. So in a similar manner, we can realize different type of alpha. So I can show you the alpha 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. Clearly, their constant phase. Everything is from 1 hertz to 1 megahertz. Constant phase is around 18 degree for 0.2, 27 degree, 36 degree, 45 degree, 54 degree, 61 degree, and 60 degree supposed to become 61 degree, and then 70 degree. Okay, these are not simulated response, these are actually practical response. Okay, so we had a practical ladder circuit, and this is what we have taken from the nature of the L cell. Then corresponding, you can see their magnitude plot. Okay, phase plot and magnitude plot. So before we move to the next section, so far whatever we have discussed, that is quite simple. That is, we have defined the fractional order elements transfer function, one by impedance function, one by fs power alpha. We have understood what is the meaning of or significance of the f and alpha, and we have discussed how this kind of element can be realized with the ladder circuit. Okay. Now here is 2 points before I move to the next section. 2 points I want to highlight. First thing first, that you can see that with this all RC ladder circuit, the entire phase is always lying between 0 and -90. So they are basically type 4 factor, fourth quadrant factor, or what we call the capacitive factor. Okay. Initially, when the fractional element was invented, or they started to find out in different type of real-time system, so all the researchers first encountered this kind of signature of the capacitive factor, and they thought this is kind of a special case of capacitance. So they initially named is a fractional order capacitance. Okay, rather instead of saying is fractional order capacitive factor, they mentioned as a fractional capacitance or pseudo capacitance, because at that time the people's idea was to look at the system from the point of deviation from the capacitance. So in many literature you will see the name the fractional capacitance or pseudo capacitance, but these are the same thing, just like the fractance or the fractional order device. Okay, this is the first thing. Second thing is that you remember when I was trying to establish the basic realization concept of the RC ladder. So actually each block of each block is giving one set of time constant. So these blocks say giving this time constant, this block is giving this time constant. Okay, now here you can see this constant phase element is bounded, this zone is bounded. Okay, now this bounded zone is actually, you can increase, but to increase this thing you have to actually increase the number of elements. So more the number of elements, the more will be your constant phase zone. So if the number of elements is going to be infinite, then the constant phase zone is also going to be infinite. Okay. Now the thing is that, so if there is infinite number of block is here, therefore infinite number of pair will be there. Now one pair is taking care of this amount of time constant. Then at the very next, there is another pair which is at infinitesimal distance, there is going to be another pair. So that is going to be second time constant is taking care, then the third time constant is taking care, the very next one. So ideal fractional element, or in which the automatically, in this system automatically there is fractional element. They are basically a combination of the infinite number of integer order pole zero pair, and therefore all time constant is involved in a single fractional element. Whether it is alpha equal to 0.5 or 0.2 or 0.7 doesn't matter. All time constant is involved in a fractional element, and that means they can remember all time constant. So that is why they can remember, which was not possible in any kind of capacitor, because it has only any RC element. Basically, the RC element, one RC element, remember only one time constant, 10 millisecond or 20 millisecond, but it inherently taking infinite number of RC elements, so it can take any, it can remember any time constant time. So that is why the fractional system has a memory, and that is the significance of the fractional unit of the second. Okay, so let's move further. So I just said that fractional element can be realized in any of the four quadrants, but when oscillator we were actually seeing that was only in the fourth quadrant, not in the other quadrant. Then how can we convert in the other quadrant? Sheriff or Austerloop or Carlson mentioned that you can do it with the help of inductor, but different value of inductor, getting different value of inductor is quite complicated, and especially in the domain of VLSI it is impossible. So what is the other option? The other option is to introduce some kind of gyrator. We will convert a capacitive nature to the inductive nature, and here comes the GIC circuit. So in the GIC circuit, we all know that additionally the GIC circuit is used to convert the capacitive element, the inductive element, mainly used for the purpose of the VLSI domain. So here you can see the GIC's impedance function is Z1, Z3, Z5 divided by Z2, Z4. If you place one inductance, one capacitance in place of Z2 or Z4, 1 by SC, that goes up and it becomes something S into a constant, which is equivalent to SL. So therefore, entire GIC block is behaving as an inductor. This is we all know, and we very much frequently use in the integral domain. The same concept, instead of using the capacitor, I am now going to use a ladder circuit here, and therefore it is going to be 1 by S power alpha C. So S power alpha is going up. You can see that S power alpha is going up means type 1 factor, right? And S power 1 plus alpha means type 2, and S power 1 plus alpha in the denominator is type 3. So we can use basically the GIC block. You can see here that I am using the Z2 position, the ladder one. So it is going up, it is becoming S power alpha. So therefore I am getting an inductive type of factor, or the type 1 factor. The entire GIC is going to behave as a type 1 factor. Only thing is that is if you want alpha equal to minus 0.3, your ladder should be chosen as a with alpha equal to 0.3. Similarly, one inductor and one capacitor together is going to give you 1 plus alpha. So it is also inductive factor, but in the obtuse angle. So if you want alpha equals to 1.3, I mean minus 1.3 because it is opposite, then I will need a ladder of 0.3 and a capacitor. So choose, put a capacitor in the Z4 position, put a factor in the Z2 position. Ultimately, it is going to give you 1 plus alpha. And if you place the factor and capacitor in Z3, Z5 position, it is going to give you the obtuse angle capacitive factor, right? So this is the how we can realize the factor in other domain. Not only that, there is another very important thing, that is you can see that is emulator factors. There is the emulator factors. This emulator factors. Can you just excuse me for 1 minute? Sorry. Um, so the interesting thing is that the emulator factors is basically a expression of resistances, the ladder factances and the capacitances. Now, if we can vary one of the resistance using a potentiometer, then the emulator factors will also be varied. So therefore, we are now not only able to realize a factor in any of the quadrant, we are also able to vary its factors value. So we are now going to get a 4-quadrant factor, and that is also in variable mode. Okay. So this is again some kind of practical plot of the type 1 factor. You can see there alpha is now varying from plus side 18 degree, 27 degree, 36 degree, just like that, corresponding phase plot. These are all practical results. This is the obtuse angle factor, inductive side, obtuse angle factor, capacitive side. And this is a whole circuit in the breadboard that was designed. So this is a GIC block and this is a ladder circuit together. So it was in the macro model. Currently, we are working to design it in the VLSI domain, okay, as a just IC level. So this is the overall system. So let's see. And this is a variation. I was talking about a factors variation. So just varying one of the resistance. So this is a factors value I am changing for some 0.2 milliunit to the some kilo unit. So factors, so just like a variable capacitor, variable resistor, we can also have variable factor. Though the factors value is varying, we can still keep the phase constant. So without changing its phase nature, what happens in the capacitor? The phase does not change, the capacitance value changes, right? So that is called the variable capacitor. The same thing is going to happen here. Their alpha remain constant, but the factors we can change. So these are variable factor. Okay. So up to this point, we were realizing the design of the fractional element, and you can see that any of you, if you are interested, you can do this thing in your own lab. You need not to buy anything. You have the paper there. You can download the paper, apply, run the code in the MATLAB. You will get the details of the R and C, and you can do the rest of the thing in your lab if you really want. The thing is that why shall we want to do this thing? What is the advantage of this thing? The domain of circuit. So that we will start with this particular example of the fractional resonator. So this is the fractional parallel resonator. So we know these are basically the same thing. We are starting with a very simple circuit because we can always go for a very complicated circuit, but let's start with a very simple circuit. That R, L, and C, that is a parallel resonator, right? This or anti-resonator, where at a particular anti-resonance frequency, the admittance will be lowest, impedance will be highest. That is the idea. So here in the capacitance, instead of capacitance, I am giving actually fractional capacitance. That means a simpler ladder. And here in the inductance, I am giving fractional inductance, and that is also basically obtuse angle fractional inductance. So this is 1 by Fc s to the power alpha, and this is 1 by Fl s to the power 1 plus beta. Right. Now, there are some calculations which is available in the paper. Let's focus on the underlying phasor diagram. What is happening? What we know in case of any kind of resonator, that is the reactive parts cancel out each other and the resistive part prevails. Okay, as it is in the parallel resonator mode, so we are working with the admittance. So this is my capacitive admittance, which will be along the positive y-axis. This is my inductive admittance. So in case of integer order, capacitive admittance supposed to cancel inductive admittance and only the conductance prevail. That was the idea. Now what is going to happen in case of fractional resonator? So instead of capacitive admittance, which is following the exactly imaginary axis, it is now tilted. It is now tilted towards the real axis by some angle. What angle? Alpha pi by 2. What is this alpha? Alpha is the order of the ladder circuit, right? So it is tilted by this angle. On the other hand, the obtuse angle inductive fractance, it is also now tilted in the not in this. It is not on the negative y-axis. It is now away from the negative y-axis, lying the third quadrant. Okay, by what angle? Now minus 1 plus beta pi by 2. Okay, so you can clearly see where the capacitive admittance is offering some real component and some positive real component, positive reactive component. The inductive admittance is now offering some negative reactive component as well. That is the most important, negative real component. So therefore, we clearly have three vectors, three free vectors, which was not earlier possible. Earlier also there was three vectors. One is, I mean, the phasor, you can say. One is inductive, one is capacitive, and one is resistive. But their angle was fixed. They are not free vectors. Their only magnitude can be varied. Now we have, with the scope of the fractional order concept, we have completely three free vectors. And by the theorem of the Lamy, all three vectors can always be adjusted to get zero equilibrium. That means zero resultant. So here the zero admittance. So with some proper calculation, we can find out this is going to be my anti-resonant frequency here in the fractional domain. Omega r to the power 1 plus alpha plus beta is going to be divided by 1 by FL FC. Basically, FL stands for 1 by L and FC stands for C kind of in the fractional mode. So no doubt it is 1 by LC with cos and sin factor. And if you just put alpha is equal to 1 and minus 1, you will see that it is matching with the integral equation. There is no problem. This is the corresponding resistance. What resistance? Now in this resistance, now we are actually going to vary also resistance. In this value of resistance, the negative real component offered by the inductive factor will be completely nullified. The real positive real component offered by the resistance and the capacitive factor. As a result, not only the reactive component cancel out, as well as real component also cancel out. So overall admittance is going to be zero. And it is going to be zero only at this particular frequency. Any other frequency, it is not zero, it is something different. As our basic concept of the quadratic factor is when the energy associated with the resonating point will be the half of the energy associated with the resonating point will be half in the band passes. So as the energy associated with the resonating point is completely zero, so the band passes has to be the zero energy only, 0 into half. So therefore, theoretically, fractional parallel resonator has infinite Q factor, because apart from this particular frequency, at all other frequencies, there will be some bypassing path. Some resistance will be there, some admittance will be there. But in this particular frequency, there is no admittance. It is completely blocked. So in other way, despite there is a finite resistance, the current will not flow. Current will completely stop, which means you just put any load here and you have a particular type of frequency signal here. You adjust this to fractal in such a way that this signal will never come down to this load. That is the beauty of the fractional parallel resonator that was not possible in the integer order resonator. This is some practical concept, a practical realization. So there is some guideline how to design all these things. So this the stability analysis and all these things. So this paper, actually I forgot to mention the paper here. The paper is fractional parallel resonator, which was actually proposed by written by myself only. So if you search with it, you will get this paper with all the design and sensitivity analysis and the practical result. So then it is the practical result, experimental result. You can see in the practical result also, we were using at the time macro model. So there was some kind of noise. Currently we are designing the VLSI based system. So we hope that noise will be less and it will also be working in the high frequency zone. So you can see in this practical macro model, it was working between the 1 kHz and 2 kHz. It is a variable resonator because I can change the fractance value. I have shown in the GIC. It's a variable resonator with all the quadratic factor is more than 400, where the traditional integer order, even in the simulation range, it cannot be more than 100. Okay, and actually it comes in the range of 5 or 4, something like that. In the fractional range, it is theoretically infinite. Even a macro model, it is 360, and our basic simulation in the IC level is showing more than 1000, even in the kilohertz range. So that is, once again I am repeating, that is the main advantage of the fractional order integer fractional order resonator. Okay, now this fractional order resonator is further utilized to design a notch filter, design a bandpass filter. Here both the case the quadratic factor is going to high. Okay, so I can show you the result of the notch filter response, variable notch filter response using a fractional sharp or tuned tuning filter, sharp bandpass filter, tuning filter response. So a comparison can be seen here for a notch filter. We know what notch filter we usually teach in our class. It is a 20 notch filter, okay, which has a quality factor 0.3, and we usually call it a very good notch filter. Or switch capacitor filter is also there of 50 dB with a quality factor 1.7. Where our proposed FON notch filter, even it is in the macro model, if we compare with the switch capacitor notch filter, 50 dB, 48 dB, its quality factor is 3 times than that, okay. Or one of the famous notch filter is fringe notch filter. In the same range, it has a 35 dB more attenuation, better quality factor. So this is all coming because these notch filters were designed on the fractional resonator, and fractional resonator has theoretically high quality factor. Okay. Similarly, this same thing can be used. So it has many applications. You guys can try with it in the IC domain and also in a macro model, also to in the biomedical application, audio application. So those are the scope of this kind of work. Then if we are almost more than half of our today's topic, so I will not much go into detail on the other things, but I am just going step by step showing some example of the advantage. For example, fractional phase lock loop. This fractional phase lock loop, just like the all other loop, there is phase detector, there is voltage control oscillator. Now we usually use a low pass filter here, first order low pass filter. First order low pass filter in the op amp we use one R and one C. Instead of C, just use a ladder. Okay, just use a ladder, and you will see that what will happen, that its lock range and capture range both increases. That is the beauty. So even from the range where the interior order PLL is not working, FOPLL is clearly can oscillate or capture that range. So again, this paper is given here. It was proposed by Tripathi et al. in 2015. So you can study this paper. The idea is fractional phase lock loop can give higher lock range and higher capture range. Okay. So you can see a comparison, multiple comparison is here. Okay. So capture range for the fractional PLL is 844 Hertz, where the similar capture range for integer order PLL is 65 Hertz. We are keeping the lock range same. So lock range is same. So it is locking within a given range, but it's capturing from the wider range and locking it at that desired range. So that is the advantage, right? So that is why the bandwidth of the PLL is much higher. FOPLL is much higher than the IOPLL. Okay. Another very interesting application, Salinity low pass filter. Okay. So we all know the Salinity low pass filter is the second order low pass filter, which we often use to realize the Butterworth low pass action or the Chebyshev low pass action. Right. And the main problem of Salinity low pass filter is that its quality factor is dependent by 1 by 3 minus k, and its open loop gain is always k. So if you really need more gain, then you really want to club another inverting amplifier, non-inverting amplifier in association with it, and therefore it is going to increase the noise and also number of elements, in the number of active elements. Instead of Salinity low pass filter, because I cannot have the gain more than 3. If we have gain equal to 3, it is going to the marginal stability, free flowing oscillation, and if it is more than 3, the simulation result is showing it is going to be an unstable system. That is, we all know the limitation of the Salinity low pass filter. But what will happen if we use a fractional Salinity low pass filter? So only difference is that instead of 2 capacitor, you are just going to use 2 fractal. These are 2 fractal I have used, and this is the Ltsp simulation, and you can see where the gain I have kept 4. Gain means this by this. So you can clearly see here the gain I have kept 4. Then the oscillation step response is basically not oscillatory. It is quite stable and very good. Its peak is within the 5%. So it is a well damped step response for the fractional order Salinity low pass filter. Even the gain is more than 3. Now here comes an argument that okay, we understand that all the fractional order element is showing us much better result in terms of fractional resonator or FOPLL or the this salinity filter, better response. But the problem is that I was using one capacitor, but now I am going to use say 4 or 5 capacitor, 4 or 5 resistors. So you are going to use a ladder. Number of elements is increasing. So how this is truly advantageous? This is the first point. And second point, they are going to ask that always we can design anything with more number. More number of R and C means more number of the order of the system. So we can always improvise our system with a better order. Then why we are going to in that mode? Let's first answer the second part, then I will answer the first part. The second question, once again I'm repeating, the argument against the fractional designer is that you are basically realizing a fractional system with an array of R and C. An array of R and C means a 5 R and set of R and C means 5 order system. So instead of single order system, you are basically introducing fifth order system, and always higher order system is bound to give you better result. The answer to this question is that yes, from that perspective, it is true that fifth order system is bound to give me better result. But technically, if I ask you to design and resonator with a fifth order system to have that high Q value, you are not going to get a closed form solution. No one can get a closed form solution with fifth order system, so that it will be tunable. It will be tunable at this particular frequency and with this Q factor. Fractional order, instead of here, if I give an fifth order transfer function, I will not be able to get this kind of small expression. This is possible because I am looking at the system from the fractional order domain, not from the high order integer order domain. High order integer domain is not going to give me this kind of closed form solution. So therefore, no prominent design guideline can be developed, which is possible here. This is the second answer. The first answer is, of course, a disturbing one. First question, that still I have to use 5 resistance, 5 capacitance. Is it going to be advantageous? Yes, in some perspective it is going to be advantageous, but not all. So therefore, we need to find out an alternative way. And that alternative way is the single element factor. It is just like a capacitor, we will be having one factor. We no need to utilize 5 capacitor or 5 inductor. And that is why for the last 15 years, this has been the most, what I can say, hot topic in the domain of the fractional order design. So it's basically started, I still going to exclude the Nakagawa Sorimachi because that was only the inception of the work, but it basically boosted from around 2005. So Haba et al. First proposed a fractal based fractional order element. Kind of the IC itself comes with a fractal structure, but it was found quite costly. So Nakagawa also in this line. So ultimately after this line, it was not much pursued. Then Bohannan first proposed electrochemical type of fractional order system, just following the nature of the traditional capacitor, and this line is still pursuing. Okay, Bohannan, Biswas, and Jesas, and Caponetto, and Mondol. And there is another line that is a solid state of a factor, because these were liquid based, which is a bulky system. We cannot really use it in the real electronic circuit. So we are just going to modify this basic idea with El Surafa, John, Agambay, and myself. We are actually trying to design some kind of solid state or gel type. I am also now trying to develop a solid state factor also, the IC type of thing, which can be used in a small electronic circuit and can also be further used as a small device or in the IC. Okay, so this is one such kind of an example. Again, it is a macro model initially, but it's a single element model. I don't need R and multiple R and C for this. So this is how we are designing. So we basically have 2 electrodes. So basically we cut it from the PCB board. This is also, you guys can do it from yourself in your lab. It is not very tough one, but of course, more good element we can introduce, better response we can do, but for the working level we can do it in the lab. So you can bring some PCB board, you can cut it small pieces. So PCB board, double flat copper PCB board. So either side there is a copper coating. So they are going to work as electrode. In between there is going to be some epoxy, which will be housing at the same time insulating either of the electrode. Then we are coating with some kind of porous material. So in this particular work, I have coated with some kind of polyimide with some MWCNT, multi-word CNT. But it doesn't matter. More easier of, I mean, if you don't get this kind of polyimide, you can always talk with your chemistry colleagues who can provide this kind of polyimide, or at least you can always get some kind of PMMA, polymethyl methyl acrylate, easily available, which can you dissolve in either acetone or chloroform, and then you have to mix some MWCNT, okay, and you have to sonicate because MWCNT does not dissolve. Then you have to dip this thing within that solution and take it out, and over the time, it depends upon the polymer, within 2 hours to 1 day, they form a thin film over the system. Then this thin film system, we are actually introducing a gel. This gel I have made using pH 9.2 gel. This is also very easy, that there is always this buffer tablet is available, very low cost. So in 100 ml, one tablet you have to dissolve, and that gel with using of agar-agar powder. This agar-agar powder we usually use to make some kind of jelly. Okay. So with the mixture of agar-agar powder with this pH 9.2, if you just heat it for few minutes in the microwave, it will form a hot solution, and that we pour in a small tube, and within this small tube we dip in this coated film, and over a time this gel set, and we just close the tube cap. There was 2 holes from where we take out to where, and we then hermetically seal it with some kind of Teflon tape and a wax, and therefore the ended things look like this. Okay, and this is going to behave as a 2-terminal fractional element. Now you use it in any of the circuit element. Just for example, I don't know whether I have a circuit element picture is there. No, not here. So basically any circuit element, so these 2 elements you can connect with GIC circuit, with some kind of resonator circuit, some kind of a PLL circuit, just like we just think these are extended or large capacitor, nothing like that. And this particular combination, you will see these details in the paper, in my paper once again. So this sustains for more than 2 years. It sustains, this particular gives me alpha equals 0.3, and there are different combinations is going to give different type of alpha value. So one who is interested, they can search for different paper is there on this topic. So you will get, and therefore the basic question that why we are going to use the fractional element, because there is going to be an array of R and C element, that entire question goes out, because now you are not going to use multiple elements, you are going to use the same formula, but with a single element. So that question does not come. And these are results. These again the notch filter. These are parallel resonance, notch filter response. These are tune filter response. You can see we don't need the RC ladder. With the single element also, we are going to get a similar kind of quadrifactor and the response. Okay. So other type of single element factor, we are now currently developing all these factor now. So we are trying to develop this kind of IC level. That was actually pioneer work in 2015. It was later the detailed work was discussed in 2020 paper. And now we are actually trying to design this kind of bendable or variable fractional element. Okay. So that work is going on, and if this work, some paper is there, you guys can also do this kind of fabrication task yourself, and that will be highly appreciated, and you can commercialize it very soon in that case. Okay. I think that as our discussion, this was actually my basic presentation, and as we are short of time, so I can skip this one. This is mainly modeling. Modeling does not come directly from our scope of the circuit. This is a stability analysis. I just want to highlight one interesting point of the stability analysis. The stability analysis is discussed detail in this paper, step by step, how we will carry out stability analysis. The only thing I want to say that I will not go into this much detail stability analysis, but this PPT will be with you guys, so you will get help from it, and you will go to corresponding paper to get a detailed idea. The concept of stability analysis comes from the basic Bibo stability, and here, just like in the integer order system, the stability where the integer system stability was on the left hand plane, here in the fractional system the stability can be more than the left hand plane. Again, depending upon the value of q, it can be also less than the left hand plane. So if it is an integer order system, sorry, it's the obtuse angle acute angle system, the stability is more than the integer stability. If it is an obtuse angle system, it is less than that. So you can see in some cases the stability of the fractional system is even more than the normal integer order conventional system. How to find out stability? Step by step it is written, but for a short of time I am avoiding. So I actually explain with some calculation. Here I come to the last topic for today, that fractional controller for a DC-DC converter. Okay, so DC-DC converter, some advantage I just want to highlight. So this is the basic concept of fractional PID controller. The fractional PID controller means one P is there. Instead of I, which is used to be Ti divided by S, it is going to be Ti S power minus M, and fractional differential is PD S power D. Okay, so this is the basic concept of the fractional PID controller, where we have now two extra variables. Initially, previously we had only Kp, Ki, Kd. Now we also have alpha and beta, and let's see that how this extra variable is going to help us to attain some extra feature. Okay. So this particular example was actually the automatic car control. In the automatic car control, that is automatic car control, what we actually need, apart from the stability, we also need the robustness and also the isodamping. So what is the isodamping? Isodamping is that we know that as we change the gear, automatic gear is there. So as we change the gear, we need during the gear change or during the starting, we need more thrust, right? So more torque. So more torque means more current. So therefore, we need to increase the value of the proportional constant. But all the proportional constant, if we increase the Kp, always it is associated with the shoot in the peak overshoot. That is not very good thing in the automatic car control or automatic car, because the moment there is going to be high peak, therefore there is going to be sudden jerk during the gear change. It is not going to be smooth car control during the gear change or during the starting. So here you can see on the fractional system controller, they can show this thing. You can see the loop gain is changing. So with the change of the loop gain, the setting time is a little bit changing, not much, but you can see the gain is 1, but then gain is by 1.3. So 30% change in gain, 30% plus or plus minus 15% change in gain, but my peak overshoot does not change. Peak overshoot was around 30%, remain around 30%. So this is one of the beauty of the fractional order PD controller. Next, another example we were showing for the fractional order buck converter. Okay, it is in the earlier there was a PD controller. This is now PI controller. So in the PI controller, fractional PI controller, we have designed, and what result we are getting? This is the uncompensated buck converter. Okay, initial settling time, there is high frequency oscillation. This is the step response for this is the open loop buck converter. The moment I am making it closed loop, the open loop buck converter has an oscillation. The closed loop, the oscillation is almost going towards the marginal stability the moment I am closed looping, but it is not compensated. There is no controller. Now here is the controller. Here you can see the green one is the IOPI, interior PI controller, and red one is the FOPI. So let's once again understand, the moment I have a buck converter, at any moment of time, there can be some change in the input flow. So therefore, we have to make it closed loop so that it follows its reference value. But the moment I am closed looping a buck converter, its normal oscillatory nature becomes more oscillatory, even it is going towards a sustained oscillation or towards the marginal stability. So that is why we use some kind of PI controller. The PI controller, traditionally we use this PI controller, we use some kind of optimization toolbox using the MATLAB, and this is a PI controller in the fractional order mode. You can clearly see the fractional PI controller has much less settling time, less peak overshoot, and less number of oscillation. Okay. However, how to design a fractional PI controller? For that, we have defined a method like genetic algorithm, Flower polynomial algorithm, convex optimization. Those papers are then there. Okay. Similarly, for the boost converter also, same feature can be seen. So in the boost converter, these are all typical example we are saying. This typical example of the boost converter, this was in the open loop mode. The moment I am using the closed loop, it becomes unstable. So we are now bound to use some kind of converter, controller, PI controller. But the green is the IOPI controller, which has sustained oscillation. Here comes the fractional PI controller. The oscillation is now much less, it is quite stabilized. So this is regarding the boost controller. So similarly, quadratic boost controller also response is given. Okay. And you can see the fractional order, the advantage of the fractional PID controller in the buck converter. We can see that here, as the input is changing 12 volt to 14 volt, in case of interior controller, there is always, the moment input is changing, input side, the output side is following the reference voltage, but there is a sudden peak. But if it is a fractional PI controller, there is no peak. No disturbance will be registered when we are working with a fractional controller. Okay. So this is the advantage of the fractional order controller. Similarly, I have shown you the advantage of the fractional signal processing circuit in the oscillator, in the PLL, in the filter, in the resonator, and there are many more things in the fractional order domain. We are now working with a challenge that all the work we have done, mostly in the macro level, we are trying to minimize it. We are trying to make the bendable fractional element, the device level, in the IC level. You guys, if you are interested, can also join with us, collaborate with us, or you can also work with yourself, standalone with among yourselves, with collaborating with other faculty members of different institute. So I hope that we will stop for today. So more or less in this discussion, we have introduced the fractional element and the circuit. We have shown how the fractal can be said as a generic circuit element and they can be realized in all four quadrants. We have shown its advantage of fractional order in high quality resonator and the filter, and theoretically infinite Q factor is possible with 20 alpha dB slope. We have discussed fractional PID controller for DC-DC converters. And ultimately, the fractional system gives you better dynamics, steady state property, rise and settling time, which improves and almost no peak under disturbance of this kind of converter. So finally, I once again thank every participant here, everyone in the audience who has given their valuable time for this lecture. I thank Gates Institute of Technology for giving me this opportunity to present our research. Thank you all. And that's from my side.
Sir, we have few participants from YouTube and they have posted their questions, sir. Can we go for questions part?
Yes, of course.
Yeah, sir. Sir, Mr. Umakant has asked that, can you please explain why it is called CPZ even though phase is not constant?
Okay, phase is, yeah, I understand. It's a very good question. Yes, it is phase. Technically, let's come to me that figure from where this question may arise. I understand it comes to this picture. See, This is not a non-constant phase. This is, of course, an oscillation is there. There is constant phase is completely an ideal concept. So phase is not even constant for the capacitor or inductor also. These we can accept as a constant. Okay, this is the deviation between, this kind of deviation always happen between the practical and the ideal. Even take the op-amp as an example, we always say op-amp has infinite input impedance, zero output impedance, infinite gain bandwidth product, but no op-amp is like that. No op-amp. It is far from infinite. Okay, some op-amp has output impedance 100 ohm, some op-amp has input impedance only 50 kilo ohm. So that is when we talk about theory, that is a different thing, because that is for the mathematical reality. Then comes the practical, and that is why in between there is simulation. This is of course the constant phase, because in contrast with that there is an RC element. That phase continuously fall from 0 and continuously come to 100 towards the, we can say, 90 degree, but it is now bounded within this zone, and that boundary, that it is bounded for a certain frequency range with a certain phase, that is for us sufficient to accept as a constant phase, and that is why we call it constant element. Of course, theoretically it is constant phase. The name derived from the theory. Okay, the name derived from this. Sorry. Just 1 minute. Yes, the name derived from this theory. Ideally, from the formula, it is exactly constant phase. What is deviation you are seeing? That is basically for the practical implementation. But this kind of practical implementation happens for any kind of circuit. Is it clear? Hello?
Yeah, sir.
Yeah. So next question, any question
Yeah,
is there?
sir.
Next.
Yeah, sir. We have another question. Which toolbox in MATLAB do we use for simulation in MATLAB?
FormCon. There is FormCon toolbox in the MATLAB. Okay. So you have to, FormCon is free toolbox. You can search, just to give me 1 minute, I can show you the name. Yes. So this is the toolbox, FormCon toolbox. You can download and put it in your MATLAB directory. Okay. So here is the documentation, one-page documentation. It's very straightforward with corresponding picture-based instruction on how to run this toolbox. It will give you all the stability analysis, time response study, frequency response study, transfer function, and once you get a transfer function from this toolbox, you can then utilize with all other MATLAB toolbox. Okay.
Okay, sir. Sir, can we wait for a few minutes for the participants to pose their questions?
Yes, yes, sure, no problem.
Okay, sir. I request all the participants to post your questions now. Sir, there are no more questions, sir. Only these questions you have answered already them.
Okay.
Yeah, sir. And most of the participants, they have given their comments as the session was interesting and it was good, sir.
Thank you. Thank you
So
very much.
Can we close the question part, sir, now?
Yes, yes.
Yeah. And now I request the convener, Mr. M. Imtiaz Pasha, sir, to give a vote of thanks for today's session.
Thank you, madam. A very good afternoon to all. It gives me an immense pleasure to deliver the vote of thanks for today's session. On behalf of Gates Institute of Technology, Department of Electronics and Communication Engineering, wholeheartedly thank today's speaker, Dr. Avishek Adhikary, for giving valuable insights on fractional order system in India, its usage in nature, networks, and different fractal element-based circuits, resonators, PLL, low-pass filter, and also the fabrication and application of single element factor. So thank you, sir. Thank you very much for spending your valuable time, sir. Thank you all.
Thank you. Thank you, everyone. Okay. Goodbye then.
Thanks for all the participants for contributing your time and present in today's faculty development program. And as usual, we will be meeting for day 3 session tomorrow at 11 a.m. to 1 p.m. Thank you. Thank you all.